What'd you do?
Okay.
With the speakers are fried. Fried the figure too loud of it,
I'll tell you what, my phone was not receiving texts the other, last week,
but.
and I restored it, and it's like a new.
Oh wait. Good afternoon, home viewer.
Oh. By the way, Blake is really sick, he's not coming to class.
He was not really sick earlier when I talked to him.
Oh no,
He's been
sick
feeling a
already.
little bad, he's got a fever, he's in bed right now.
Really?
He's got the shakes.
Shakes?
And the sniffles. Yeah.
All right.
Blake's coming with us. That's a sick hat, by the way.
Yeah, and
Dude,
he kind
you
of
like
got
Blake's
like
hat?
a-
I stole it from my buddy's house.
But who did?
Eric's house?
Yep.
Yep. Yeah, oh yeah, you better.
Okay, so we're moving on to chapter 4 today, looking at the implications of an axial load. So if I have some kind of a sample, it might look something like this. That's not good. Let's try that. Okay, something like this. And I apply a load up here at the top, and I have a little attachment point, and I pull on that, a little eye hook or something. Then there's going to be a stress distribution. And if I plotted the stress distribution, let me use a different color for that. If I plotted the stress distribution right here close to that end point, I would find that there is a concentration of stress in the center where I'm pulling it, which kind of makes sense. Right? If this were a piece of rubber and I were pulling on an eye hook, it would bulge up at that point where I was pulling it. But as I get further and further away from that point of application, that stress will tend to become more uniform. So this idea that the stress distributions and the associated strain distributions become more uniform the further away you get from the point of application. It's called St. Bennett's principle.
Sorry, can you repeat real quick what those dotted lines are?
Those are the stress distribution.
Stress.
So here I have a high stress in the center and a low stress at the edge.
Okay.
But as I get down further away, the stress becomes uniform across there. Okay, so it's not, there's no numbers associated with that, that's just a relative distribution of stress. Okay, so St. Bennett's principle says that these stress distributions become uniform when sufficiently removed from the region of load application. So sufficiently is a relative term, depends on the nature of the material and so on, but when you're sufficiently far away, the stress and strain distributions become uniform. So we're going to take advantage of that from the vast majority of our applications. So for us, we're going to focus on the average stress and strain, right? So this is the average stress distribution. Okay? We're going to focus on regions where we've achieved this average distribution. We're not going to work, for the most part, so close to the points of load application that we have these non-uniformities. Okay, we're going to take advantage of St. Bennett's principle, and we're going to be working in this region down here. However, you'll notice that that value, let's call that sigma B, and an associated strain B, whereas this is sigma A, and an associated strain A, is going to be different than the average stress distribution down here, sigma C and strain C. So in this case, sigma C is going to be greater than sigma B, and epsilon C is therefore going to be greater than epsilon B. Because we've reduced the cross-sectional area so that the stress is higher, and therefore the strain is higher. So even though we have uniform stress and strain across the sample, as long as we're far away from the load application point. That doesn't mean that that's uniform along the sample. We can still have variation along the sample. We just don't have it, we just have no variation across the sample. Okay? So, this sigma c then, sigma point c, or sigma in general, is going to depend on the load applied at that particular position x. Okay, so x is the variation along the one-dimensional axis, divided by the area, which is a function of x. Area can vary, as it does here in this picture. Right? Area varies as a function of x. Load could also vary as a function of x. In this case, I've just applied a single load, but there could be friction, for instance. One of the example problems we'll use has friction. If I were squeezing this sample between two rubber blocks and pulling on it, there would be friction acting, right? So there'd be a distributed load along here, so that P varied at different points along here. Right, because the distributed load thing, we have to integrate the distributed load to find the total P. So the P is a function of x, just like A is. Similarly, so we're sort of essentially taking, what we're doing is, let me take this little section here out. So that little section is experiencing a load that depends on its position. That little section has a dimension delta x there. It has a cross-sectional area, A, that also depends on x. Right? And as I pull on it, it's going to stretch by an increment like this, right? So as I get this small enough, this becomes dx, and this becomes d delta. Remember, delta was the amount of stretch. Okay? So, if I look at the stress on this particular piece, it's P as a function of x divided by A of x. And the strain on this particular little piece, what's the strain going to be? On just that little piece that I cut out of the sample.
Changing, or d delta over d.
Right. D delta over dx. And the change in length divided by the initial length. Good with that, right? Okay. So each little piece is going to experience a different d delta in response to the applied load. So if I want to know what the total delta is for the entire sample, I want to know how much my whole sample stretches, I'm going to have to integrate all these d deltas. So that's going to be the integral of epsilon dx, or I could rewrite that as the integral of sigma over E dx, because epsilon is related, if we're in the elastic regime, so from here on over, we're assuming it's elastic. Right, so we're in that linear proportional region. But sigma is px over ax, so it's really the integral of p of x dx over a of x e of x. That's my total displacement. So I have three things that vary as a function of position. And I would have to integrate those three functions. Now obviously that's going to be kind of ugly. Right? If we really had this load distribution, the area changes, all some kind of functional behavior, we'd have this big ugly interval. But in reality, most of the time, there will be sections over which those things are constant. Right? Or at the very least, over which P of X varies, but A and E don't. Okay, so E will vary if we change material. So if I have a hunk of aluminum attached to a hunk of steel, then E changes. A changes, obviously, in this way. P changes, I mentioned friction is one possible way in which P could change. I could also have another hole through here with a cable pulling down on that hole. Right, so I have a different P down here than I have up there.
P is the load.
P is the load. Yeah, sorry, I forgot to label that up here. Right, so P is the load that's applied. But in reality, there are going to be sections of it that are all uniform. So what I'm going to do, what I'm going to end up with then, is in most real cases, delta is going to be the sum over a bunch of I number of sections of the integral of that, which is P sub I, L sub I, over A sub I, E sub I. Where it's uniform for each section, and then there is a step change to some other condition for the next section.
So, does the E actually change very much? I thought that was a property.
E would change if I had two different materials. So if I have a brass bolt mated to a steel bolt,
Gotcha.
right, so that's what's going to change.
But if it's a uniform material, then it won't
Then
change.
E is not going to change.
Okay.
And you'll see as we get into some examples, A and E often fall out. Okay. So by convention, delta is positive if it's a tensile condition and negative if it's compressive. So in other words, if I'm elongating the bar, then delta is positive. If I'm compressing the bar, delta is negative. Because if I take a bar and I pull on it, one end is moving to the left, one end is moving to the right. Right, so there's no way of saying right is positive, left is negative. There's no convention for direction in that sense, because you've got both motion in both directions. So delta is by definition positive when it's tensile. So any elongation of the bar, delta is positive. Any compression of the bar, delta is negative. Okay. All right. One more thing, and then we'll do some problems. The other thing that's going to be helpful here is the concept of superposition. We use this in statics. You know, when you're talking about multiple loads, one of the analytical tools in statics is to use superposition. What is the effect of this load, and what is the effect of this load, and then let's add them together and we find the total effect. You guys remember doing that in superposition in statics? Did you? You never did superposition in statics?
We did superposition in
Yeah,
electronics.
and stuff.
Okay. It really works in any superpositions, and it works in any linear system. Right, so again, tying together the mechanical and the electrical, it's the same idea. If you have any kind of, as long as the system is linear, that means that the thing you're trying to measure, in other words, delta, or sigma, you have the stress or the displacement, whatever it is, must be linearly related to the applied force. So anytime you have this linear relationship, then you can treat each force independently and then take the superposition of those forces. Okay? And the other constraint for superposition is that you have an unchanging geometry. Now, you look at that and say, well, anytime there is deflection, there must be a change in geometry, right? I apply even the slightest amount of load to this pen, and it compresses. Minutely, but it compresses, so it changes geometry. So here, by unchanging, we mean no significant changes, so like things like buckling or bending. Right? So if there's a significant change in the geometry, then superposition doesn't work. Because in the case of buckling, one force might not buckle it, and the next force might not buckle it, but the combination of the two might buckle it. right? And so then we're no longer working in this sort of superposition regime. It's no longer a linear regime. Okay. So that's the effective constraint. But superposition allows us then, if we had friction over here, to separately look at the effect of this externally applied load and the effect of friction. And then add together the total delta from both of those. Okay? All right, once again, I forgot to turn on the computer.
XKCD for this.
Okay.
So it's
What's that?
an XKCD, is that what it is?
XKCD.
That one.
What? What's XKCD?
You know what it is?
No, what are you talking about?
It's like a,
Like cartoons?
it's like a
You've never
engineering
seen it?
mathematical.
Oh, yeah, I know what you're talking about.
Mhm.
David showed us one for Bernoulli's principle. Or was it Bernoulli?
Oh, yeah, it was like,
Yeah. It was like what. to
your
say-
parents are Santa Claus.
Yeah, it was like what to say to a student when they've been questioning your aerodynamics skills. And it was like, the correct answer. Like, that's a good question. Let's explore more. The wrong answer.
No, let's keep moving on.
Like, let's just move on to this topic. The really wrong answer. Your parents are Santa Claus.
And then we,
It's just not quite as funny when you're telling someone about it as when you're looking at it.
Yeah,
Mm-hmm.
that's true. But the video was good too.
Okay, so there's our first problem.
Wait, there's a video?
4.5.
And, yeah, this one? Or you're-
So, if you look at 4.5, so we have an assembly that consists of a steel rod CB, so there's one material, and an aluminum rod VA. So we have two rods, two different materials mated to each other, and joined by a coupling B. So essentially they're both screwed into B. Right? If the rod is subjected to the axial loadings at A, so in other words, there's somebody pulling on the end of the aluminum rod, and the coupling B, but there's then something pushing to the left on the coupling, on like a collar, so there's like another, you can imagine another cylinder on the outside of this rod pushing to the left. Then we need to find the displacement of coupling B and end A. And the dimensions given there in the drawing are the undeformed, the unstretched dimensions.
Oh, so there's an actual second force on the coupling B
Right,
pointed towards the wall?
right, so there's one force pulling A out, and there's another, like you can imagine a cylinder, a hollow cylinder riding on the outside of that shaft, AB, that is pushing to the left. Okay? Everybody understand the problem and how it's drawn? So our job now is to find the deflection delta for points B and A relative to the wall C. Okay? Everybody got the problem? All right then, so what do we do first? As we say, Blake's not here, so
Free body diagram.
somebody's got to fill in. Free body diagram.
AB.
And so, what's that?
Of A and of AB.
Just of AB. Okay, so free body diagram of AB. So where do you want me to start? Stop, just to the left of B or just to the right of B?
Left of B.
Or right of B.
I would start stop just to the right of B.
You don't want to put the 6 kilonewton force into a free body diagram?
Right. So I've got, what is that, 18 kilonewtons pulling out here, and I have a total dimension of this thing of 2 meters. Right? So there's an internal force pulling in this direction of 18 kilonewtons, which means that that member is just under tension. Right? So I stop just to the right of, infinitesimally to the right of B, so that I get this nice simple system.
Okay.
that make sense?
Yep.
Okay, so now what? There's my free body diagram. What am I trying to find? What's it asking for?
Find the stress inside AB.
Yeah, what am I trying to find? What's it asking
Ego.
for? The delta. I was trying to find delta. So I need to find delta, no matter what piece I'm looking at, I need to find the delta. Right? So in this case, now that I've got this particular body as I've chosen it, do I have, is P changing? No, I got a uniform P, right? There's no extra P's. Is A changing for this sample? No? Is E? These are all constants, I can pull it out. Delta for AB, therefore, is just equal to P L over A E for this particular. So I could go through and P A B L A B A B E A B. I don't want to be exact. So I can find the delta for that end of the bar. So what's PAB? The 18 kilonewtons. What's LAB? 2 meters. And actually, I'm not going to put the units in there. We'll just assume that everything's SI unless I specify otherwise. Okay. What's the area of AB?
36 pi millimeters.
What's that?
36 pi millimeters.
36 pi millimeters.
Right.
Pi
You got
r
that.
squared. Right. Okay.
Six
So-
squared times pi. Or
Right.
Yeah.
Right. So let's just, I'll just leave it in there as 0.006 squared times pi. So we can leave it in SI units. Again, the point is not,
Okay.
not put millimeters in there. What is E for AB? 70 gigapascal. So 70 times 10 to the 9th. Good? Plug in the numbers, do the math. Of course, they don't have the answer here. That doesn't help.
Is kilonewtons or should we have just meters?
So you're right. If we're going to do times, so this is times 10 to the third. Right.
Oh, yeah.
And then the answer should be in meters, so if we put everything in SI units. What do you got? Somebody got something? That one it doesn't have.
Got 4.55 times 10 to the -6.
Not buying that.
I don't think that's right.
No.
Not meters.
I actually just got that too, for what it's worth.
Oh,
Oh, you know why you got that? Because you didn't do 18 times 10 to the third. You just did 18. That's what I did. I didn't see it.
Ben, yeah.
Ben is speaking, he's
Four, four.
channeling, you're channeling Ben
Yeah.
now. He's speaking
It's
through
4.5 times 10 to the 3.
4.5 what?
Five.
Making mistakes.
Give me 5 sig figs total. That's what we're doing.
5, okay, then 4.547 3.
Times 10 to the 3 or millimeters. Now we're good? Okay. So that's the, now, has it been, is it positive or negative?
Positive.
It's positive. Right? Okay, that tells me the length, the change in AB. Is that the total change?
No, that's just the change in AD. You gotta find the change in BC now.
Right, gotta find the change in BC as well. So the change in BC, how do I find the change in BC? Am I gonna be able to do it from that free body diagram?
Where are we gonna make out?
Another free body diagram. Okay, what free body diagram am I gonna use?
CB.
CB? Okay, what are the forces acting on CB?
You have 24 kilonewtons going to the left at B. Right, 6 kilonewtons plus 18 kilonewtons.
Look at those, look at the picture.
I look at the picture. Notice you have a normal force in from the other free body diagram that has to go, it's pushing on B.
So if this 18 is being, if this is pulling to the left on AB, then there's an equal and opposite force pulling to the right on BC, right?
Right.
Okay,
Right,
so
right.
what do I have at B?
You've got 12 going to the right.
12 going to the right. And then on the left? Anything else?
Normal force of 12.
Reaction force there. Right? So I could have looked at that and also recognized up here, since I've only got the two forces, the reaction force at C must be 12 kilonewtons to the left. Right, and then I wouldn't have to worry about B at all. I'll just find the reaction force from the total drawing and then apply that at the other end, at B. And that way I can stop this just to the left of the applied force. Okay, but same physics one says in the other. Okay, so now I want to find delta BC. What's delta BC? Well, it's going to be the same thing, right? Because now we have just this uniform condition again. So it's PBC, LBC over ABC. It's as easy as 1, 2, 3. All right. Should do that on camera. No, I'm just joking. It's all right. We really don't want to see that.
What's going on?
Okay, what is PBC?
It's a monster, isn't it?
What's PBC? That's PVC.
Oh,
Okay, 12
okay.
times 10 to the
PVC
third.
is what we print our circuit boards on.
12 times 10 to the third. What's LBC? 3. What is ABC?
Same as above.
Same as above.
6 squared.
0.006 squared times pi. And what is EBC?
200 times 10 to the 9th.
200 times 10 to the 9th. And what does that get me? Well, if I look at it, that's going to, well, no, I can't look at it because the 200 changes. So what does that get me for a value? $1.5 something. 915? Okay, are we happy with 1.5915 millimeters for delta BC? Right? And both of them are in tension. So then the total delta is just the addition of those two. What was that, 5, 6 point, bit of a number? 14 millimeters. Make sense? Okay. Then, let's go on to the bottom one. Tackle the bottom one. Any questions before I erase? Actually, I'm going to leave that up. Okay, 414. We have a post, a Douglas fir post, buried in the ground. And it has a diameter of 60 millimeters. So it's roughly 2.5 inch diameter post. It is subjected to the load of 20 kilonewtons, a compressive load of 20 kilonewtons, and the soil provides a frictional resistance that is uniformly distributed along its side of 4 kilonewtons per meter. Determine the force F at its bottom needed for equilibrium, and also find out what is the displacement of the top of the post with respect to its bottom B. We can neglect the weight of the post. All right, what do we do first?
Free body diagram.
Free body diagram. Okay. Here's my post.
Blake told me to say that.
You did.
He was channeling Blake.
Channeling from
Channeling
Blake's
your
diagram into,
All right. What forces do I draw?
we can start with the 20 kilonewtons.
20 kilonewtons pushing down. What else?
You can go do the friction force going up
Friction force going up. Where do I apply that force?
at the, I mean, it's applied evenly, so I guess you could apply it in the middle at 4 times 2.
So that would be 8 kilonewtons. Okay. Any other forces?
There's a force pushing up from the bottom.
Right. Force F that we're trying to find. Okay. Now what?
Why is it only 4 times 2? Because I remember earlier when we did the example of like the pulling the, I don't
Right,
know, the bolt on a
because-
concrete.
Because they gave us the units of 4 kilonewtons per meter. So they've already taken into account the area, the surface area.
So if they gave it to us in 4 kilonewtons per meter squared, then they expect us to multiply by that.
Right. Then we'd have to go ahead and multiply that across.
You define the area.
By the circumference area.
There's a circumference, like
You
a
say multiply,
surface area.
right, by surface area though, right. Okay, that makes sense? Right, so what do we do? Sum them. So, sum of the forces in the y direction is F plus 8 minus 20 equals 0. F equals 12 kilonewtons. Now part A was just a piece of cake, easy peasy. But you figure it should be because it's actually the part B that's relevant to what we're doing in this section. So part B is what is the displacement of the top of the post with respect to its bottom B. Neglect the weight of the post. So now what do? We're going to find the displacement. Okay, well, come back over here, right? Does the area change? Does E change? Does P change?
Well, yes, it does actually. It changes when you hit the 8 kilonewtons. And it changes again when you get all the way to the bottom.
Actually, there is no, when you hit the 8 kilonewtons, it's distributed,
Right.
right?
But does it,
P varies as a function of X. What's P right here at the top? 20. What's P at the bottom, right before I get to the bottom? Hmm?
oh, right before you hit the bottom?
Right before I get to the bottom.
12.
12. What is it in the middle? If I take this little section out here.
It's going to be,
Right.
Halfway?
Right. Is it halfway?
Yes, it's 18.
Right. So the friction is distributed uniformly.
beautiful.
So the top half experiences 4 kilonewtons of friction, the bottom half experiences another 4 kilonewtons of friction. So if I were to take a little slice right here in the center, it would be experiencing a compressive load of 16 kilonewtons. 20 minus this 4. right? So it's a uniform, there's a linear function. So P is a function of X. So I'm gonna have to get an expression for P of X
It's just 8x.
to be able to integrate.
Right?
I don't know, is it?
Yes.
What's X? Where's X zero?
X is 0, we can say where X is 0.
Right,
We can say
where's X
zero
gonna be 0?
at the top,
Okay. X equals 0 at the top.
and positive X is down.
Right, so that's X. Okay. So, P of X equals.
We'd say P of X equals 8 kilonewtons. Well, no, you would say it was 4 kilonewtons per meter, so it would be 4x, or 4kx.
Well, let's just make it 4X kilonewtons.
You could just add the k in the end.
Right, I'm just putting it in the unit. 4X kilonewtons. Everybody okay with that? Really, only 2 people participating, everybody else is just sort of taking it. Jesse, you okay with that?
Yes.
Just
Ben, are you okay with that?
I've done some calculations,
That's
they,
okay.
they came out wrong, but.
Yeah.
Clayton?
I can't take a nap with my pants.
Nobody is going to stand up to Colin and say, wrong, sir.
Well, maybe we all just are wrong.
No, or maybe we're all just too lazy to.
Double check as we're.
P equals 4X kilonewtons. So when X equals 0, what is P?
No, that's not P.
Plus 20.
Push 12, push 20.
Plus 20.
Push 12.
All right.
Minus 4x plus 20.
There you go, minus 4X plus
Oh.
20. Or we could write that as 20 minus 4X
We can.
kilonewtons. There we go. Now we're all happy.
Oh, nice.
Okay?
I was happy before, but.
We're just a happy bunch. We're happy all the time, even when we get stuff.
I was an ignorant.
Happy end, you know, stomp your feet. Okay.
There's a new version.
Oh.
Let's not digress. Okay, so now we have an expression, right? We have to come back here to our delta, but because P is a function of X, we have to less delta as the integral. But we're going to say 1 over, we're going to extrapolate or extract first 1 over AE. Because A and E are not functions of X. So we'll pull them out of the integral. So all that's left is P of X dx. So that's 1 over AE, we'll plug in AE in a second, times the integral of 20 minus 4x dx, which is 1 over AE times, what is the integral of 20x, or 20 minus 4x dx?
20x minus 2x squared? If I can remember how to integrate.
It's been a while.
It's been a while.
It's been a
20x
while.
minus 2x squared, okay? And then x is evaluated from where to where?
0 to 2.
0 to 2. Right? Okay, so the 0 is nice, everything disappears, so we just worry about the first term. So we're left with 1 over AE times 40 minus 8. So delta is equal to 32 kilonewtons divided by, what's A? What's that? What units are we working in here? Okay, so 0.03 squared times pi, and I'll just go ahead and erase the kilonewtons and make it times 10 to the third in the numerator to make sure we don't make the same mistake again. And what is the E? What's E?
Should we look it up?
Can we? I don't know, you got a book?
That's negative.
And I guess you're not gonna be able to look it up. Anybody got a book?
I can tell you, I can look it up on my iPhone.
You have a book?
I have a book, so I'm good. You guys are sucking wind.
Fucking wood.
Yep. Douglas fir. Yep, right there.
It's really in there?
Mhm. They wouldn't have given you a
Yeah,
problem
that's
with
right.
Douglas fir if it wasn't in the book.
Well, I didn't know if they were like, you must round to this type of wood.
You must
Yeah, 'cause
round to this kind of wood.
That's assumed generally in all problems. Rounding to a certain type of wood.
13.1 gigapascals.
It's just a very like,
Okay, so that gives us a final value then of 0 point, yeah.
Each copy.
.864 millimeters. Everybody good with that? Yes or no?
I'm good with that.
Jesse?
I'm good with that.
Clayton?
Why did we add the times 10 to the 3?
Because it's 32 kilonewtons. Everything's in kilonewtons.
Oh.
So you good with that? Ben? All right, Caleb, last chance to be different.
I'm so good with that, I'm gonna leave.
Well, unfortunately, once again, somebody should have had an issue with it.
Ah.
There is a problem.
Classic.
There is a problem. What is the problem?
Same time.
What is the problem? Something simple.
I'm negative.
A negative.
Ah,
It's a
yeah.
compression. It's under compression,
Oh,
Nice.
dang it. Why didn't I think of that?
Ah.
right? Delta is negative when it's compressive. Yeah, right.
Oh, there.
It's all my fault. Okay? Is that good? We're actually done 5 minutes early today.
Oh, wow.
That's the only time to practice.
I will be on time.
Hey, have
My
fun,
game.
sliding around in the rain.
So you have a game tonight?
Yeah.
Oh, here?
Oh, wow.
Yeah, wait, is it here? It is actually.
Oh, man, I don't
It
think
was gonna be up in Fort Wayne, but it's on grass up there, so they moved it here.
we have to go.
See you guys.
See ya.
Girls game last night too, and then the girls game tomorrow.
Here,
Yeah.
on the turf. Do we have, is the practice field turfed?
Yes.
The football practice field is, I do the soccer.
That's what I mean, so the football players can practice if they're playing on the side. If they're-
Right. Well, actually, Is it? is it turf? Clayton,
What?
isn't the practice field grass?
You got the football field, it's turf, you got the
Track.
soccer,
The old soccer field's not turf, but there's that other one,
the track is not, but no one does anything over at the track.
no.
And then you go across by Randall, and that's obviously not either.
No,
but
that's
they-
not,
But
but there's
isn't that
another
thing,
field.
isn't that thing to
and
the
then
left
we-
of the stands, as I'm sitting there watching the game, isn't the thing to the left of the
Yeah,
stands,
is
isn't that
that-
turf or is
That's-
that
I
grass?
feel like it is turf,
I
maybe.
think it's-
Like, are you saying behind the
Like,
the
no.
scoreboard?
Right, yeah, right in front of the.
Right behind the scoreboard?
Right.
No, that's not
No.
turf.
Okay.
Not behind the scoreboard, behind,
It's like a practice field.
like in